You all know how to describe a point in the xy plane, also known as the Cartesian plane. So you have, this is the x-axis and this is the y-axis. So this point here, assuming this point is x and y, so I'm abusing notation, I'm using x twice, but it's fine. So this point is just x and y. So this way of describing the point is called the Cartesian coordinate system. Now there is another way that we can describe this point. We can think about how far the point is from the origin. We're going to call this r. And then we can also think about the angle it makes with the x-axis, right? We're going to call it theta. So instead of describing the point with x and y, we describe it with r and theta. Okay? So this is called the Cartesian, the polar coordinate system. Okay? So if you have a point, say you have a point that makes, let's look at a bunch of points. Okay, so assuming we have this point right here, okay, and it's one unit away from the origin and makes an angle of 45 degrees. For 45 degrees is pi over 4. So this point right here, its coordinates is gonna be, so assuming this is 1, its coordinate is gonna be 1, and then pi over 4. And then let's look at a point that is around here. Okay, assuming this point is 0.5 units away from the origin, and it makes an angle of 270 degrees. So this angle is 3 pi over 2, right? So that would be the coordinates of the point, and so forth. Okay. Now, this polar coordinate system is very useful in describing regions that are circular in shape. Circular regions, okay? Okay, what do I mean? Now, think about this. If I have this region, I'm trying to make this line as straight as possible, but it's giving me a tough time, but I'm gonna get it. All right, good. Okay. So consider a circular region. Let's start with a very simple circular region. Let's start with a semicircle. So we have this. And this is the region. if we completed this circle, that's a circle, not an oval. This is the region we want. But let's assume we completed the circle, and the circle is a circle of radius, say 2. 2. How about 2? 2, -2, and so forth, -2. So the equation of this circle is x squared plus y squared is equal to 4, right? So if we want to describe that region, we might first of all solve for y. So y becomes square root of 4 minus x squared. Okay? And it's plus or minus square root of 4 minus x squared. But since we are looking at the top part, this is the part that's where y is positive. So we're just going to go with square root of 4 minus x squared. Okay? So we're looking at this line. The region is bounded by this curve, which is y equals square root of 4 minus x squared, and y equals 0. Okay? So for instance now, if you have a region, think about a region, so something like a region that has this as r, as or an integral that has r as its region of integration, dx, dy, dA, would now be the integral y from 0 to square root of 4 minus x squared, and then x goes from -2 to 2, then dy dx. There's nothing wrong with this. This is fine. But you notice that we're going to be dealing with this. This has a square root in it. Okay? So that's normally how we know, the way we know how to deal with circular regions. Okay? But now, hold on. What do I want to do? No, I don't want to do anything. Let me try another thing now. But assuming we look at this circular region, let's look at a bunch of circular regions. All right. Let's start with the one we have there. I'm going to draw a bunch of them. Okay, this is... All right, so we have this region, call it R. Okay. Let's try another region. Let's try and then let's go for a third one. Let's go for this one. Let's see, we have, well, why not? Okay. So instead of doing all the exercise we did here in order to describe these regions, if we know their radius, so for instance, let's assume this is 2, and let's assume this is 2 and this is 1 here, and this is also 2. Okay? The region here would just be the region, first of all, let's describe, I'm jumping around, but let's describe this region. Let's describe the green region. Let's see how interesting it is. It's R equals x, y, such that y is between 0 and square root of 4 minus x squared. And then x is between -2 and 2, okay? But now, let's use polar coordinates to describe these regions. Let's use polar coordinates. I'm going to say alternatively, use polar coordinates. That means we are seeing them as polar regions. They're polar regions. So instead of xy, we do r theta. This is r theta, such that r is between 0 and 2, and theta is between, let me go. It's so hard to see everything here. I don't want to encroach. So, okay, good. And then theta is between 0. Actually, 0 should be lower. Is between 0 and 180 degrees, which is pi. Okay? Now, this one, so that's our first r. This r over here, r here, is equal to r theta, such that r is between 1 and 2, and theta is between 0 and pi over 2. Okay? All right, now this one is a little easier, or it should be easier. Well, the other ones were easy too. R here is r theta, such that the radius is between 1 and 2, and then the angle theta is between 0 and 2 pi. Okay, so that's how we describe regions in polar coordinates. Now, our goal is to use this to perform integrations that involve circular regions. In order to use that, we need to get ourselves familiar with a theorem. This theorem will raise a question, but we're not going to worry too much about it. Theorem, and I'll explain the question to you. Double integral, this is a integral in polar coordinates. So assuming you have a polar region like this, polar region, call it R, and R goes from R equals little r equals alpha or equals A to little r equals B. And then it goes from theta equals alpha to theta equals beta. Okay, so this is our region R. Thus, R is r theta, such that R is between A and B, and theta is between alpha and beta. Okay, where beta minus alpha is less than 2 pi. So the difference can't be more than 2 pi. The stretch of the angles can't be more than 2 pi. All right, this theorem is telling us that if we want to find, I'm going to move this up a little bit, move everything up, because I'm about to write in the edges, and that's not a good thing. All right, I'm going to move this up. Okay, the theorem is telling us that to calculate an integral over this region, if we're going to calculate an integral over r of f r theta dA, okay, this is the same thing as integral from alpha to beta from a to b of f of r theta dr d theta. But then there is a little r here that you have to include. Okay. This r is what I said is a question that I expect you to ask, you know. The answer comes from the derivation of this formula. We're going to look at that in class. You know, hopefully we'll have time to do it. But you can see this is kind of intuitive. This says integral over the region r, where that's r, is just alpha to beta, and then a to b of f of r theta dr d theta. That's more intuitive, but that's not complete. It's not correct. To make it correct, you have to actually include this little green r there for things to make sense. All right, let's do an example. Example, more examples. Let's find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. All right, and I'm going to sketch this region. So we have a paraboloid. I'm going to sketch the paraboloid first, but okay. 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 So this is, you know what? I think it's actually visually more interesting if we make the z-axis go through the origin. That's more correct. All right, so we're gonna make this. Yes. Okay. Y, X, Z. Okay. So this paraboloid is Z equals 1 minus x squared minus y squared. Now, the xy plane is Z equals 0. Okay, so we have our region in the xy plane is this region right here, the circle right here. The circle. So this would be our region of integration. This would be our R. Okay. So let's look at R in the way that we're familiar with. So our R is just the circular region. R would be x, y, such that x squared plus y squared is less than or equal to 1. Okay. Why did I say it's less than or equal to 1? Because how did I obtain this region? I obtain it by finding the intersection of the paraboloid of this paraboloid equation and this. All I did is set it equal to 0. You end up with x squared plus y squared is equal to 1. So this is the region where this is the line. The green line is where x squared plus y squared is equal to 1. Okay. So the region now will be the region where x squared, this region will be where x squared plus y squared is less than or equal to 1. So that's our region. Now, this is just, this is at a closed disk, right? This region is, let me see, copy this, put it here. So I can go in here and I can sketch. And I can sketch my region. Okay. So we can go ahead and sketch the region here. Well, I did it green, so let me make it green because in the main diagram I had it as green. It's fine. So this is our region. This region R. Okay. So this is a circle, and I'm going to write a circle is not a function, but we can break it up into two functions. We can break it up as y equals square root of 1 minus x squared. This should be obvious. And then this one is y equals square root of negative square root of 1 minus x squared. So the top part is y equals square root of 1 minus x squared. The bottom part is negative square root of 1 minus x squared. Sorry, the top part is just square root of 1 minus x squared. The bottom part is negative square root of 1 minus x squared. And how did I do that? All I did is solve for y in x squared plus y squared is equal to 1. Right? And then solve for y. Okay. So we have our region. Let's go ahead and do our integration. We're looking for volume, so this is our f of xy. This right here is our f of xy. Z equals xy. So we're going to use the form R f of xy dA. Right? So if we're going with Cartesian, using Cartesian coordinates, or what we also call rectangular coordinates, let's see, oh Lord, using Cartesian coordinates, this is what we get. We get integral, double integral, y goes from negative square root of 1 minus x squared to square root of 1 minus x squared. And then our f of xy is just 1 minus x squared minus y squared. And then we have dy. And x goes from -1 to 1. And then we have dx. All right. This is doable. There's nothing wrong with this. But the problem here is that this square root sign is going to give you some problems when you're trying to do the integration. All right? So we're not going to go this, we're not going to go that route. We're going to try to use our polar coordinates. Coordinates instead. All right, our region R is just a circular region. So it's r theta such that r is between 0 and 1 and theta is between 0 and 2 pi. So the volume we're looking for, let's see again. We're looking for copy. Oh shoot, something is wrong. Something is wrong. I did something wrong, okay. Okay. Okay, so we want to compute this integral, double integral. We need to set it up first in terms of r and theta, and that's gonna require some work, but once you do it once, you'll be fine. So let's do r, our f of x, y, dA. This is gonna be r. Let's change it to, let's still make it r. But we have 1 minus x squared minus y squared. Let's call it dA. Now, there is something I should have mentioned a while ago, but I kind of forgot. I don't know why. Let me go back and mention it. This is how to convert between x and how to convert between the polar coordinates and the Cartesian coordinates. Okay, so if you look at this, you see that this forms, we can form a right angle triangle over here. Okay, and x is the adjacent, and the y from 0 to x is the adjacent, 0 to y is the opposite. All right, so we have that x over r will give us cosine of theta, and y over r will give us sine of theta. So for this reason, we have x is r cosine theta and y is r cosine theta. We're going to be using this throughout. This is very important. So I'm going to copy these two things and I'm going to bring them here because they're important. We're going to make use of that. Okay, now, so our polar region, we can change this to polar. We can go, we deal with the r first. We deal with 0. R goes from 0 to 1, and theta goes from 0 to 2 pi. And then we have 1 minus r cosine theta is the same thing as x squared is r cosine theta squared minus r sine theta squared. And then we have dr d theta, but don't forget the extra r. Okay? Now, the next thing we have to do is to simplify this. This is 0 to 2 pi, 0 to 1. So this is going to be 1 minus r squared cosine squared theta minus r squared sine squared theta times r dr d theta. All right, keep going. 0 to 2 pi, 0 to 1. So you have 1 minus, you can factor out an r squared, and then you're left with cosine squared theta plus sine squared theta, and then you have r dr d theta. Keep going. 0 to 2 pi, 0 to 1. R cosine squared theta plus sine squared theta is 1. So this will just give us r minus r cubed dr d theta. Okay. If you do perform the integration for r first, you have r squared over 2 minus r to the 4th over 4. Go from 0 to 1, 0 to 2 pi d theta. All right. If you plug in 1 and you plug in 0, actually you end up with, you can factor out a 1/4, 0 to 2 pi d theta. So this is 1/4. Then you have theta, 0 to 2 pi. And this will give you pi over 2. Pi over 2. All right. So that's that. I suspect you will have some questions, but we can talk about that in class. All right. Next question is evaluate the integral r 3x plus 4y squared dA, where r is the region in the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. All right. So in the first problem, we're looking for volume. We needed to know how to set up volume, all right? And we needed to know that integrating a function, the surface on top of an area gives us the volume that surface forms with the area in the xy plane. But in this case, we're given a function and we're just asked to find the function, to find the integral of the function, and we're given the region R, okay? So we begin first of all by looking for the region. In the other case, we began by making sure we understand the figure and deciphering the region ourselves. In this case, we don't need to do that. We just need to figure out what the region is. I'm going to draw the region here. The first part of the region is a circle of radius 1. Circle of radius 1. The second is the circle of radius 2. All right. X-axis, y-axis. X squared plus y squared equals 1 is a circle of radius 1. X squared plus y squared equals 4 is a circle of radius 2. And we're told that it's the upper half plane. So we are looking at this part. We're just looking at this part. Okay, you see that? So this is our region. That's our region. So our region R, let's write it in terms of the polar coordinates. It's going to be r theta, such that r goes between 1 and 2, and theta now goes between 0 and pi, 0 to 180 degrees. That is our region. All right. Now we can set up our integral. The integral we're looking for is this integral right here. I'm going to copy, put it right here. Okay. So we can now set up our integral as integral theta goes from 0 to pi, r goes from 1 to 2, 3x is 3r cosine theta, and 4y squared is 4r squared cosine squared theta, right? And then r dr d theta. Okay. So your work, your job is to do this computation. The answer I got is 15 pi over 2. So I want you to try this, do it yourself, and ask me in class if you have questions, or correct me in class if I'm wrong. Okay. All right. That's polar coordinates, integration in polar regions. I will see you in class.